Applications of the parametric equations. Ah, that was terrible. So I was wondering as I was doing this problem about the Ferris wheels, right, and where that name came from. So here we have Miss Gallen and Miss Getz, before social distancing, of course. We're riding on a Ferris wheel with a radius of 30 feet. Right, and here's a picture of the Ferris wheel, and here's some equations. But let's figure out where these equations come from. The lowest point on the Ferris wheel is down here at what we'll call 6 o'clock, and it's 10 feet above the ground. We, Miss Gallen and I, are over here, right? We call 3 o'clock, and we're going to call that when we're going to start our clock then. We're going to call that when time is equal to 0. So I could have an equation that models that, right? We did that in AF, right? When we studied periodic functions. One of the first things we did was, Ferris wheels are a great application problem for this. But I want a parametric equation so that I can get time into the situation, right? So if we, let's see if I can make a pen color that's a little bit, if we think about this circle with a center here and a radius of 30 feet, and it goes clockwise, so if we travel up here, right, this is still 30 here, isn't it? So this radius is also 30. If I drop a perpendicular, this should look familiar, right? Do you see that planning in connection with curriculum? You did this in AAF. I gave you circles and had you draw triangles in them, didn't I? Now I'm going to erase this horizontal looking 30 because remember that 30 went all the way out to where Miss Gallen and I were when time was starting. But now time has started to move on and we've gone around the Ferris wheel and I've dropped this perpendicular down here, meaning that 30, this length here is not 30 anymore, right? The length from the perpendicular to the center. But from the center all the way out to where Miss Gallen and I now are is still 30, right? So let's see if we can take these equations and figure out where they came, what happened. Where did they come from? So I'm going to draw that triangle out here. Right, the horizontal side that is now shorter than 30 and the hypotenuse that is 30. And I'm going to draw this central angle here. And you learned that in geometry, right? About central angles being equal to the arc they intercept. And remember, the arc is out here. So, using our triangle trig, this is the horizontal component of our movement, and this is the vertical component of our movement. So what do we know here? Right? Don't you know that the cosine of that central angle is equal to the horizontal component over the hypotenuse, right? So how about you get the horizontal component by itself? What are you going to do? You're going to multiply by 30. So look at what we have up here. The horizontal component, which we call x, is equal to 30, the radius, times the cosine of the angle, right, which represents the horizontal movement right here. And then what is this? That sub-zero, remember? This is the initial horizontal position. At time equals 0. That's what that 0 means. So now, can you figure out what this equation is? Wait, I'm just going to do the same thing, aren't I? The sine of that central angle is equal to the vertical component over the hypotenuse. And then I'm going to get the vertical component, which we call y, by itself by multiplying by 30, which is, of course, the radius. And that's what this says. The vertical component of our movement, which is what we call y, is equal to the radius. Our radius is 30, times the sine of the central angle, times the time that we spent. Right? Here's our parameter t, the time of the rides. And then this again is our initial position, initial vertical position, right? At time equals 0. That's what initial means. Okay? So these are the two equations that we need. I'm going to erase all this, okay? These are the two equations that we need to set up this problem. So let's see what else we have here. So I want a parametric equation where the horizontal is equal to 30 cosine theta plus 0, right? And at time equals 0 is, they told us that Ms. Gallen and I were here at time equals 0. So our horizontal position is 0, right? Considering this a 0 position. But what about my vertical position? Is also the radius 30 times the sine of the central angle. But what is my initial vertical position? Well, this distance is 30, right? The radius down to 6 o'clock is 30, right? That distance is 30, but what do I also have? To the ground, which is 10. So over here, this is going to be plus 40. Oh man, I forgot my t's, didn't I? Now the issue with this equation, this is swell. I've filled in the r. I have filled in the initial positions. Remember, I'm supposed to have one equation, x, with one unknown. My unknown is already here. My other unknown, right? I'm writing a parametric equation in terms of t. So I need to figure out this angle theta. Grr. Grr. What am I going to do? What information up here in your words haven't you used yet? Now I know I want to use the model, so I'm not going to use 22 yet, right? 22 is in seconds, so can you figure out where that's going to go eventually? Right? And I want to find my position, which is my horizontal and my vertical position. So I need these equations to find my horizontal and vertical position at 22 seconds. So the odd man out here is theta. So what do I need to do? I've used 10 already. I've used that. I've used the 30 feet. What haven't I used? 1 revolution every 10 seconds. What does that tell me? I have 1 revolution 1 revolution every 10 seconds. What does that say? 1 revolution every 10 seconds means what? Doesn't that mean your period, right? Oh, throwback. That my period is 10 seconds? Well, how does that help? If my period is 10 seconds, right, what do I do with that information? What am I doing here? 360. 360 is what? All the way around, divided by my period. What do I get out of that? Remember, this is degrees. And period is unitless. So I've got 36 degrees. 36 degrees is the angle, right? Because to go all the way around, 36 degrees must be my theta. So now let's go erase theta. And put 36 here. Now 36 is not a special angle, which usually they aren't. So this is obviously a calculator problem. I put this into my calculator. And I say x of 22 and y of 22. And what do I get? I got 9.3 here, feet. And y of 22, I got 68.5. So let's get out your calculator and practice modeling and putting these things into our calculator. I wish I knew a way to get this calculator up without making all my... Oh, and by the way, this is when I said I wondered where ferris, why is it called a Ferris wheel? If you go to this link, I have an article on who Ferris is and why is the Ferris wheel named after him. It's pretty cool because it goes all the way back to Roman times, which is not where Ferris came from, but pretty cool. All right, so let's hit mode and put ourselves in degrees since we were dealing with degrees, and put ourselves in parametric. And let's put our equation in here. And our equation was, I have it written down because it's not here, right? What was my x equation? My x equation was 30. Excuse me. Cosine of 36 t plus 0 and 30 sine 36t plus 40. Now think about our window. What should our window be? right? That number you should recognize as 2 pi. I don't want to do that. How long was our ride? One ride was what? 10 seconds. My t-step is pi over 12. Don't really care as long as it's small. But my horizontal, what should my horizontal be? Should go from like 0 to... What do you think? Actually, let me go a little bit, maybe like this. Let's see what that looks like. My y min, 0 to 30. Nah. Plus that 10, 40? Oh, no. I got to go higher than that, right? Because I got to go the other side of the radius. So let's see what this looks like. Oh, freak. What did I do wrong? Right, that is one sad looking Ferris wheel. Right, my x is messed up. Now I knew it was. Right, so what is my x? What do I need my x to be? Yeah, think about this, right? My horizontal position at time equals 0 is over here, but right, don't I have to go... Let's see if I make it kind of, what does this look like? Oh, there we go. That's a little bit better. I probably went too far. I didn't need to go all the way to 100, but... And now notice when you hit trace, the power of, yes, I've got my position, my horizontal and my vertical position, but I've got my parameter time in here. So as I start to move through time, you can kind of see where Ms. Gallen and I, where our seats are going. And again, with my screen, my Ferris wheel looks a little oval, but I think you get the idea. Now notice that if I did this, I could have just hit trace 22, right? What does this mean? Why would I get an error when I tried to put in 22? Something's wrong with the time. Oh, wait. What did we tell the calculator the only times we were interested in? Right? We were only interested in 0 to 2, but what did we ask it for? This was only one ride. So let's make it 3 rides. Now I'm going to go here, over here, and make this so you kind of can see it trace more than once. Make the little bubble. Notice there was no shading like there was in rectangular mode. Right, there's us starting off at 0. There's our Ferris wheel. We're going all the way around. Back to the beginning of where we started. There's our second ride around. And where are we at 22 seconds? Probably somewhere around there. I forgot it was enter. I was going to be very dramatic and stop it over here, but I hit on instead of enter. Whoops! I can hit enter again and make it go. And now notice it'll stop though, right? It stops based on the time interval I give it. But now when I hit trace and 22, I won't get an error. Right there I am, 9.3-ish and 68.5-ish. Pretty good, huh? All right, keep that calculator out. We're going to be using it a lot today. Projectile motion. So that motion was just moving along, right, a Ferris wheel. There was an engine creating our movement, right? We didn't have any control over it. But there's lots of other things in our world where the motion is dictated by, we want to model it by some kind of what is giving the motion. So maybe we have an object and we're launching it, right? Whether it's something that we're playing, or a basketball shot, hitting a baseball, shooting a rocket, you know, basically anything that goes up and then comes down, right? We might want to get time into the situation. We want position and time. So some of the problems we're going to be doing will introduce this idea of projectile motion. So we're going to have to do a little more kind of baby physics here. So velocity, notice that the velocity vector, right, v is a vector. Notice, compare this with the notes that you just took before, where we were dealing with the horizontal component was r cosine theta. And the vertical component was r sine theta. Well, in vector land, remember right? This was the magnitude or the velocity for dealing with speed, right? So that is velocity at time 0. If you have an initial position at time 0, the horizontal component is exactly what we did before, right? Breaking this vector up into and just taking out its horizontal and vertical components. Right, so you won't be surprised. Oh, wait. What the hee-haw is that? Alright, hold on a second before we spaz out. I recognize that part. Right? Now, think about our Ferris wheel when we had the radius, right? My horizontal component was just, whoops, I don't want no freaking laser. My horizontal component was just r sine theta plus y sub 0. But Ms. Gallen and I got on a Ferris wheel, and, right, we had an engine that was moving us around, like, constantly. What is this? You know what this factor, if you will, is? This factor is, on Earth, the effect of gravity. Now, I guess I shouldn't say on Earth yet, because this G here, we're always going to assume we're on Earth, so this G is going to be a constant, right? Earth's gravity. The negative comes from the fact that gravity acts in a downward, right? It pulls down on us, right? You throw something up, it comes down. The 1/2, you'll see where this 1/2 comes from when you take calculus. It's actually pretty cool. I'll just say the word derivative out there. But this G is going to be a constant for us, right? And there's different G's for different, you know, different planets that scientists and physicists can figure out given atmospheric pressure and blah, blah, blah. But on Earth, depending upon whether you're measuring in feet or meters, 32 feet per second is the effect of gravity on Earth, of course in a downward motion, and then you take, for the negative, then you take half of that. And 9.8 is if you're measuring in meters per second. So look how fancy that equation looks like, but you've seen so many of these in Algebra 1, just not in parametric mode. Negative 16t squared plus, you know, 60t plus 4. And you did lots of stuff with something like that, right? That's where it came from. This is all where it came from. Okay. So how are we going to use these? You don't have to copy this down. I do have for you these examples typed out along with the notes that you just saw. And they're on a handout. Let's see, do I have it? Whoops, that's not what I wanted to do. Let's see. Where is open? Sorry. I just want open recent. Where's open recent? Oh, there we go. Here we are. So this is on our classroom already. Parametric modeling. Right, so, that's not the one I want. All right, kids, you're just going to have to trust me that it's on there. This is a waste of our time. So anyway, you don't have to copy these down if you don't want to. You can print out this and work on a handout that says in-class examples. All right. So a boy throws a ball out of a window with an upward speed. Now why he would throw a ball out a window, I don't know. But the height of the initial throw is 75. Find a parametric model that represents this situation. So the first thing I want to do is draw what the heck is going on. So this kid is inside some building, I don't know, practicing social distancing, right? So he's at some window. Oh, I hear my granddaughter is coming, I think. Lucy, oh, I hear her crying. So here is a window. Right, and I want to, he throws the ball up, right? So, and I don't like that they say initial throw, but anyway, what this interpreted mean is that the window is 75 feet, right? That's my feet. That is my initial position. So the parametric model, and then they're going to throw the ball up, so certainly it is going to eventually come down. So what's confusing about this one to start off with, and I hesitated whether I should start with this one, is that since the kid is just reaching out the window and throwing the ball up, right? It is going up and then coming back down. Now we are in all these situations, we're going to ignore the fact that there may be wind blowing right and left, rain, hail, whatever. He's just throwing the ball up and the ball is coming down. So what is my horizontal position? Right? My horizontal position doesn't change. So what's kind of cool here is that you can, oh, I guess that wasn't Lucy. You can, you can kind of choose an arbitrary in this situation. Right? As position, I can kind of pick it to be whatever I want, but what is my vertical component? Gravity, negative. Feet, right? We were dealing with feet, so which number do I use, the 32 or the 9.8? Right, 32, but remember you have to take half of that. Then I need to put in my initial velocity, and what was that formula? Right? Well, if I'm throwing it up, isn't the angle, right? What is so the initial velocity sine theta t plus my initial position. Right? The height of when they first start is 75 feet. So that's why the 75 is right here. But what's going on here? I think I have v sub 0. What do you think that is? And notice the units on it, feet per second. So I feel like I can put that in. But what angle am I talking about? What angle, right? What angle does this represent? Right, 90 degrees. And what is the sine of 90 degrees? Oh, snap. Just a 1. Excuse me. So, there's my parametric equations. I can choose any constant here. So why wouldn't I choose 1? I'm not going to choose 0. I don't want to be multiplying anything times 0. Actually, the 0 wouldn't matter anyway, but when I go to the calculator, hopefully you'll see why I chose 1. Now, I could graph this in rectangular mode, right? And I would just say, well, I'll call this axis t, and I'll call this axis y, right? And I would have some parabola that looks like this. We did this in algebra, right? And I would have told you in AAF, I would have said, you know what? You should dash this part, right? Dash this part because the reasonable part of the domain, right? The reasonable part of the domain would have been here, right? And we would have found the x-intercepts and the maximum and blah, 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 blah. And that's all great, and that's perfect. The power of having a parameter, though, is that now I can graph something that looks 2D, but I can introduce time. So go to your calculator. So this time I want you to put 1 in here, right? Because just a constant, my horizontal doesn't change. And then here, type -16. And think about your window. What do we want? Right, again, I have a small t-cept, so that's fine. Hey, if you're throwing something up and it's coming back down, that's not going to take very long. Let's say 5 seconds maybe. And I'll adjust that if I have to. I'm just kind of thinking here. Now remember my x, right? My x is just constant. It doesn't really change. So I think I'll make that go the same as my time. But what about my y? Remember, you're starting at a height of what? 75 and then throwing it up. Now, I don't know how far I can throw, so I'll leave it at 100 right now. Let's see what this graph looks like. No! Did you see that? Let me slow that down a little bit. Up and back down. That was pretty cool, huh? Let's see what happens when I hit trace. At time equals 0, so do you see how this x doesn't matter? If I'd made this x 0, then you would be graphing, you would see that along the building. So I just made it as if maybe he's holding it out, right? The kid is holding it out 1 foot from the building maybe. So at time equals 0, you're 1 foot from the building, 75 feet from the ground. You threw the ball up, the kid threw the ball up. So there the ball went up to a maximum height, and then gravity took over and brought it back down. When does it look like it hit the ground, huh? Somewhere around, right, more than like maybe 3.5 seconds, something like that. I could change my t-step, but I could also do, shockingly, some math, right? Set the vertical component to 0. Crazy. All right, let's move to the next one. A 400-pound piano is dropped. Dropped is going to be very important to our equation from the top of a 100-foot building. This time they are asking me more than just to model. They are asking me when, which is a time question, and how high will it be after a certain time in seconds. So what should we be thinking about here? Well, firstly, drop. Thank goodness, right? I can't imagine you're going to be throwing a piano. You know, at Delaney's, Devin and Delaney stayed their first years in a dorm up in Boston, and they had a piano drop every year. I think at the beginning of school, I don't know. I know, college kids, whatever. Where do they get these pianos from? Anywho, drop means you aren't throwing it. We call that free fall. Free fall means you aren't giving any initial velocity. You're only letting gravity do its job. That's nice because then it means the free fall equation in feet is just the effect of gravity, which is negative 1/2 of that 32, plus your initial position. I don't know why I started writing that out. That's, of course, your vertical equation, right? So I'm going to kind of do the same thing here with my horizontal. My horizontal isn't going to change. I'm just dropping the piano. Devin, when did you guys drop the piano from Baker? Beginning of school, end of school?
No, it's in April. It's for drop date. It's like April 20-something. It's drop date, so you drop the piano off the roof.
Oh, what does drop mean?
It's
drop
like when you can drop your classes by.
Oh,
the last day that you can drop your classes.
I get it. Nerds. All right, where do you get the pianos?
Oh, one might donate them. We had actually too many pianos. We didn't know what to do with them. Yeah.
That's really funny. All right, so I'm going to make my horizontal component constant. 1, 2, again, 0. You can. This is just for graphing, so you can see the graph better. And then our y component is free fall. And we're in feet. So that's why I use -16 t squared plus my initial y position. What was that? Okay. So what are the questions they're asking me? They're asking me, when will this hit the ground? So like I alluded to in the last one, when is a time question. Hit the ground is a vertical question. So I want to make 0 equal to -16 t squared plus 100. So t squared is going to equal positive 100 over 16, right? Because it was -100 but divided by -16. And then I'm going to take the square root of that. Check my math. Right? 2.5 seconds. Now I know this is an exact number, but still, when we go to the calculator, right, a lot of times when we're going to use these in our calculator when the numbers aren't so nice, I'm going to store this in alpha A. How high will the calculator be after the ground? I'm sorry, after 1 second is also a right? Vertical position question at a given time. So this one is just y of 1. Y of 1 is 84 feet. So I didn't need to use that 2.5, but if in any of their other questions, they were asking me where I had to input 2.5 anywhere, I would be, saving those so that I can preserve all the degrees of accuracy till my final answer. So sometimes kids will ask, what the heck is this with why can we do this free fall and we're not really taking into account the weight? Well, Galileo, way back in the day, he was like, no, look, weight doesn't matter, and he went to the top of the Leaning Tower of Pisa, and he dropped 2 objects that were of different weights, and sure enough, they hit the ground at the same time. But he did not do a ball and a feather. He did 2 spherical objects that were relative. They were different weight, but they were relatively the same shape, right? So then Newton came along, and Newton, with his math, calculus, and physics, he theorized mathematically that even if you had 2 objects, right, that were different weight and different shape, that the only thing that would affect how fast they fell in a vacuum, the absence of air, would be gravity, so that they would hit the ground at the same time. So this video is by Brian Cox, which is so hilarious because I was playing this video seeing if I liked it, and Mr. Getz was in the other room and he goes, "Hey, why are you listening to Brian Cox?" And I was like, nerd. So no, he's a very he has a lot of videos, physics videos. So if you're ever questioning something that happens, you're not sure what's going on in your physics class, that wouldn't be in Mr. Getz's physics class because he would explain everything very well. But you can always Google Brian Cox and his videos. So let's watch this for a minute or two. Oh, why isn't my volume on? Oh, sorry. Technical issues. My volume's not on. I thought my volume was on. Oh, I wonder if it's because I'm filming. No, that happened yesterday. Let's see if I can do it this way. Will this work? My audio will work this way, maybe? Ah, I'm sorry, kids. Pause for a second. My bad. See if I can figure this out. Is that what I need? There we go.
And it is
Sorry. Thank you for being patient.
Chamber. It's used to test spacecraft and the conditions
Isn't
of
his accent awesome?
And it does that by pumping out 30 tons of air. Galileo's experiment was simple. He took a heavy object and a light one and dropped them at the same time to see which fell fastest.
Duh.
In this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So, in order to see the true nature of gravity, we have to remove the air.
Okay, we dropped 2 millitor in the last 30 minutes.
But once it's complete, there's a near perfect vacuum inside.
This is so cool.
6104 manual, 10% open. Station 1, go for drop. PCB 30-1, pressure set point at 240 psi. We are go for drop. 10, 9, 8, 7, 6, 5, 4. Cameras on. 2, 1. Release.
How cool is that? Love the dramatic music too.
Exactly. They came down exactly the same. Wow. Look. Look at how they hit right there.
Exactly.
Back on the side.
Exactly the same.
I love when people are so into what they're doing. Like, look, he's so excited about this. I think that's so cool.
Isaac Newton would say that the ball and the feather fall because there's a force pulling them down. Gravity.
Now, I stopped it there on purpose because there's a little bit of a, I was going from Galileo to Newton. Brian Cox here goes also into Einstein. Little mind-blowing about gravity. I'll save that either for you to look at or wait until you get Mr. Getz. All right. The next problem. Not gravity. This time we're going to stay horizontal because the last two problems were just right. We had our horizontal component be just an arbitrary constant because we were just talking about vertical position changing due to gravity and velocity. So here we're talking about playing capture the flag. I have to admit, I didn't do a lot of capture the flag playing when I was growing up. We did a lot of hide and seek, a lot of Spud, a lot of Foursquare when we played in the street. Mr. Getz played a lot of capture the flag, he says. So I have two runners standing opposite one another 50 feet away. Notice these numbers, velocity, speed, obviously because but speed is the absolute value of velocity, and of course you're running. Now they are running in different directions, right? So you need to think about that. But runner A is faster than runner B. I'm sorry, the other way around. Runner B is faster than runner A, but runner B hesitated for just a microsecond there. So first they want me just to come up with two sets of parametric equations to model the situation. Then we're going to go to our calculator and graph it, and then we're going to do both the math and calculator to determine which runner wins. So first let's take care of runner A. Runner A. What's runner A's horizontal component? Now I'm going to do this relative to the flag, right? So I'm going to call this 0. This is like my 0 point. So runner A is starting 50 feet away from 0, but in which direction? I probably should have done the velocity first, shouldn't I? Now I've got no gravity, right? So this is just plus 9 times t, right? I've got no angle, right? I mean, if you want to think about it, my angle's 0, right? And what's the cosine of 0? 1. So I guess I should have said that. Now, how about my vertical component? What's my vertical component this time? Well, I don't have a vertical component, right? How about runner B? Runner B has a horizontal component. Also, initial position is 50, but 50 to the right, so I'm going to call that positive. And then they're running in the opposite direction, right? So this person's running in the opposite direction, so I'm going to say that's negative 10t. Oh wait, but am I going to call it t? Should I call it t? But it's not just t. We're going to find out if the, excuse the smoothie being make, right? So this speed or velocity, remember this is a velocity. Now they gave it to me as a speed, but I made this positive, right, the velocity positive to indicate going to the right, and this velocity I made negative to indicate running to the left. And then I also had to account for the starting later, right? So the time that this runner started was always 0.1 slower than when this one started, right? So there's my two parametric equations. Now, let's answer the question before we go to the calculator. Why can't I say that word? Which runner wins? Well, that's when the distance, I want to find out when runner A gets to the flag. So what position is that? Position 0. So the seconds would be what? 50 divided by 9, right? Which is approximately 5.5 seconds. A little bit more. And then how about runner B? Also, when do they get to position 0? I got 5.1 seconds out of that math. So, who ended up winning? So even though runner B hesitated, maybe they were just trying to be nice, winner B still is the winner, right? Winner, winner, chicken dinner. Right, so it only took runner B 5.1 seconds to get to the flag, but it took runner A 5.7 seconds. Right, so she who hesitates is not lost in this scenario. By the way, when runner B gets to the flag, how far away is runner A? What is that? What do you think that means? How should I figure that out? Right? When is a T question. Runner A would be, right, at the same time, 5.1 seconds when runner B was at the flag, how far away, what was the horizontal position of runner A? So that's just saying what is x of 5.1. And again, I just used my calculator, and I got a negative. But what does that mean? That means the position left of the flag still 4.1 feet away. Desperately trying to draw somebody running, and that looks terrible. All right, the last two problems, last couple of problems with the throwing the ball up and then down, piano being dropped, runners running horizontally. I've either had a 90-degree angle, and I was dealing with the sine of 90, which is 1, or I've had a 0 angle, or 180, however you want to think about it, where I'm dealing with the cosine of the angle, and the cosine is of that is 1, right? So now what happens when we are launching at an angle?
I will.
Okay. Doing anything else?
So, talking about hitting a baseball,
Yep.
I get, right, what do you think 4 feet above the ground is? Right, 4 feet above the ground sounds initial to me, right, initial height. And, oh, I have a nice velocity here, 125 feet. So again, I know which gravity thing I'm doing. But they want to know about, will the ball clear? Now, I don't know if you know what that means in baseball terms, right? Basically, will the ball go over this wall? But the wall is 400 feet away. Oh my gosh, there's so many things going on here. Hold on a second, sorry, I gotta answer a text. Do-de-do-de-do. I mean, it's so nice. We do still try to keep up with one another, right? And I have another friend whose father is in I'm sure many of you are coming across situations like this, right? His father is elderly and in a nursing home, and they just found a case there. Oh, scary, scary times. Okay, Ashley, so what's going on here? So remember what we dealt with before, right? I have the same equation, right? We have our x position is from the formulas I gave you in that first slide, and you see it if you've printed out that paper. I have it on the back, right? Initial velocity times the cosine of theta, t, and the vertical component has gravity, which for us is going to be negative 16 t squared, plus the initial velocity and the sine of the angle that it's launched. And again, we were dealing with ones for these with our initial problems, plus the initial, oh, I forgot the initial position over there on the x. So what's happening here with Ashley? So I have Ashley sitting over here and hitting a baseball, right? So here goes the baseball. And the initial velocity is here. And then the horizontal here's, right, the horizontal component remains unchanged, right? And much like the Ferris wheel problem, we're going to consider here, which is why I ended up not writing it, the initial position, right? At time, we're going to consider the horizontal to be, right, a 0 position, right? So from initial at time 0, the horizontal, the ball is just going to continue to go in this direction, right, horizontally. But vertically, after the initial velocity, right, once the initial leaving the bat, then you know this is going to follow some parabolic path, right? Right is going to be the vertical. And the question is, there's some wall here. Will the ball land before the wall? Will the ball hit the wall? Will the ball go over the wall? So, how do we figure this out? All right, so let's look at the x component first. So the x component I didn't mean to put a 0 there either on either one of these. Sorry about that. The x component, I've got the velocity, right? My initial velocity is 125. But again, I have to deal with this angle. Ah, I forgot my t up here too. I do have my initial vertical position, don't I? All right, so what's this angle? Well, hopefully my drawing's giving you a little bit of a hint.
Oh, hi, how are you?
Right?
No, that's great. Awesome.
Draw that triangle there. And what is, right? What do I have going on here?
Okay. Sure. Okay.
Right? Isn't it true that the cosine of that angle is the horizontal over 125? Oh, I'm such a moron, aren't I? I was deriving this thing for you. They gave me the freaking angle. Ugh. This is where the 35 degrees is. Sorry about that. I was giving you the derivation of the formula, which I did already. That's 35 degrees. So I don't have to solve for it at all.
Thank you very much. All right, that's great.
So put these values into your calculator. Ah. So x is 125. Cosine, make sure again I'm in the right mode. Yes, degrees. Cosine, 35. $125 times sine 35. So those are your two, so about 102.4 and 71.6. I already forget what that number is. was it 90 something? You'll have to remind me. I forget what that is. But notice they asked me, will the ball clear a 25-foot wall that is 400 feet away? Well, what do I want to do there? First, I need to know when, right? When will the ball be at 400? Well, what equation should I use with that? 400, right? Think about the drawing that I had up there, right? And then the wall is horizontally 400 feet away. So I'm going to go to my x equation and put 400 in there. Which again, I know is, I think, about 102.4 if I've calculated that right. If I mean, remembered it from my calculator. So t is 400 over that amount, which I did write down. And I got about 3.9. This I need you to store in alpha A. Right? And I literally, on my calculator, I did type 125 cosine 30 down here. Because I'm going to use this number. So I now know the time that the ball is going to get to 400. So at that time, now I need to say, well, what height will it be? So when will the ball be 400 feet away? I answered that. Now I need to know how high will the ball be at that time? At that time. So that's going to be horizontal. How high is a vertical? So go to the vertical, and I'm going to plug in, I'm going to write 3.9, but on my calculator I'm going to type A. And I got 39.9 out of that. Now I'm going to go to the calculator and show you these things. But I just wanted to write down on the screen what we have here, so you had that by you while we go to the calculator. Now, what if I also asked you? What if I asked you a clarifying question? What if I said, do you think oh wait, so what do we answer? So will it clear, right? Will it clear it? Right? So the ball will be 39.9, so the answer, I should have answered this over here. Yes, it will clear the wall. Right? By how much, actually? How much will it clear the wall? Right, that's just minus 25. They didn't ask me this, but I'm just saying. So it's going to go 14, it's going to clear the wall by 14.9 feet. So do you think the ball is catchable? Could could Ashley, oh no, Ashley hits it, so could some baseball player standing at the wall, right, standing over here, make this incredible leap up and catch the ball? Right? And now you need to give me a reasonable answer here. Now you want to tell me that they've got bionic legs, or I don't know, have a trampoline or something, but being 39.9, right, the wall is already 25 feet high, and the ball is up here 14.9 feet higher. I don't think so. I think this is a towering home run, as they would say. Alright, so let's go to the calculator and look at a couple of these things. So 125 cosine, making sure again that you're in the right mode, radians versus degrees, negative 16 squared plus 125 sine of 35 degrees plus 4. Now, what should my window be? Right? How many seconds do you think it takes? Well, what was that time that we got? We got a time to reach the wall at about 4 seconds, so I don't know, 5 seconds is fine, I guess. Maybe 6 seconds, maybe I'll give it one more. Small t-step is good. How about the x? How far do we want the x to go? Right? Well, the wall was 400 feet, so let's go a little bit further. And then how about y? How high do you think that ball is going to go? Right, well, we had, what, a height of 40? So I don't know, staying at 100 is pretty good. I have the little, like, ball, so it should look like a, right? Oh, whoops. Something's wrong. Something's definitely wrong with my equation there. What'd I do wrong? Ah. Calculator's frozen, I think. Oh no, there we go. There we go. There we go. What did I do wrong here? Oh, did I have my parentheses wrong here? Oops. Help me figure out what I did. Negative 16t squared plus 125. I see what I did. Didn't catch that. I bet you did, didn't you? 335. So again, I'm not sure about how the calculator likes those t's. I think the t needs to go inside, or it doesn't matter. Let's try this, since I only want to change one thing at a time when I'm trying to troubleshoot, right? See if this gets me what I want. No, so it must be, what the hee-haw? Well, let me then go change the t's again. There we go, Laura. All right. So here we go. Ashley hits the ball, and there's the path of the ball at each time, right, as time goes along. So do you remember how we would, in rectangular mode, we would, like, if we wanted an intersection, we would graph like a constant y value? Well, look what happens when you do second calc there. It doesn't have that capability, right? It has the value, and then these things have to do with calculus, but it doesn't have an intersection value, option. But check this out. Look what happens when I put, I'm going to put 400, I'm going to graph it simultaneously. This graph of 400, which is how far the wall is, And then I'm going to hit 25. Right? What's 25? What does that have to do with the problem? That's how high the wall is, right? And then I'm going to hit 25 times time divided by 6, which seems kind of weird. But what I'm doing is slowing time down. Now I wonder if you can figure out why 6, right? See what I made I made 0 to 6. If that had been 4 seconds, I would have divided it by 4. So I'm just trying to slow time down. And this is just showing off. You don't have to do this, but this is just kind of a cool feature. Especially since I couldn't figure out where my T should be. I'm going to graph this in simultaneous mode. And watch what happens now. There's the ball hit, and there's the wall. Now the wall isn't obviously growing at the same time. But you can see that, right? There's how, right? There's the wall, and the ball is clearly going over the wall. Now that wasn't that impressive for a ball that we knew was going over the ground, but let's say we start changing things up. Like, well, what if she hit the ball at a 33-degree angle? What happens? Right? She's hitting the ball at a different angle. Will it still clear the wall? I don't know. What's going to happen? Ah, barely went over it. Right? Let's change it again. How about 31? There goes the ball. Oh, snap. I don't know. Not sure. Right? Now, of course, I can do trace and go over there and see if I can figure it out. But, of course, your calculator, especially with the pixels and what my t-step is, not sure exactly, but your math would give you this, right? If you solve those equations like I did before, you know exactly, does that hit the wall? Bounce off the wall? Does it land in front? So somebody, right? Somebody should certainly be able to catch it. Is this going to bounce off the wall? And should the player then back up for the rebound? All this kind of stuff is, believe me, these are analytics that your baseball teams pay math people to figure out for them. All right, so I think you should be fine to attempt these the problems that I gave you from the book. I think you have enough to do that. And again, these are not assigned. You don't have to do them, right? But I think they won't be. I think they'll be fairly easy to do and easy to figure out with the examples and using the examples in your calculator that I've given you. Make sure, remember, when you use a calculator that you show setup, right? Notice that when the stuff I wrote on the screen was, right, I didn't plug in alpha A. I plugged in, right, I wrote the numbers, I wrote the equation. Am I plugging in a number, or am I setting an equation equal to a number? Show that setup, and then you can use your calculator to verify and do computations and graphs for you. Okay? All right, I hope you have a great rest of your day, and don't know when I'll see you, if I'll see you, but please know that you are in my thoughts always. Take care.